Okay, back to calculus. Thank you again for indulging me. I hope to improve those lectures over time. So you are my guinea pigs. Huh? Last year's class were guinea pigs for calculus. This is already the first iteration of this course for me. Although last year I was only allowed to give like 10-minute lectures. That was the active learning. So that was really painful for me. Because I really wanted to give lectures. Well, now they have it now. That's partly why I did these recordings. I hope everyone on YouTube feels dizzy. That's about as good as it's going to get. Okay. That's not what I want. Okay, so I already showed you what a version of an improper integral is. So everyone now has to snap back into life, because you're going to need to know this. Okay, so here's our motivation. Here's a curve. It looks like this. It's given by y is equal to ln x over x squared. And I want to ask, what is the area bounded by this curve in the first quadrant? Now, the limit of y, the limit of y as x goes to infinity is 0, I believe, right? So we're truly going to hit the axis at some point. Is this going to be an infinite or a finite amount of area? This is interesting, right? Because now I'm saying, suppose I've run a fence, right, to fence in the ocean, and the fence is infinitely long. You guys okay? Something weird about the ocean? Fence? Oh, that's what happens when you live abroad for a while. I also say bagel weird, pillow, and milk wrong. Milk? Who says milk?
Milk?
Milk. I used to say milk.
How do you say it?
Milk, but I think it comes out milk occasionally. And bagel, bagel. I think we're a little bit off topic, but so infinite area. Is this infinite area or not? Is it possible to bound a finite amount of area with an infinitely long fence?
No. Wait.
By
Infinite long fence?
This fence is infinitely long. Is it possible to bound a finite area?
Oh, yeah.
But the infinities aren't equal necessarily, are they?
But you can still bound the finite.
Just say I don't know.
I don't know.
Okay, let's try and find out. Okay.
No, man.
How could we what is the quantity in question that we need to deduce? Jeez, write the integral that would give me the answer to this.
Oh, the integral of the function.
Oh yeah, oh sorry. Okay, 1. Can you give it to me now?
Yeah, probably.
Okay, so tell me what it is.
So integral from 1 to infinity of the function, whatever it is, ln x over x squared.
Okay, I told you we can't do this. This is illegal. Okay, so for the time being, I'm just going to do this.
And
Exactly. Well, let's be consistent because we usually integrate from A to B.
b.
Okay, so I'm going to write B.
And b approaches.
Exactly. Okay, so let's resolve this. What is the integral of ln x over x squared? Or give me the technique that you would use. Crying isn't a technique.
Crying.
Can you go parts?
By parts.
Yeah.
Okay, so which should we choose by parts?
Like u ln x.
So you want u to be ln x, which means du is 1 over x dx, which forces dv to be 1 over x squared dx, which forces v to be 1 over x. Okay, so that means this integral is limit b goes to infinity of uv, so that's minus ln x over x minus the integral from 1 to b of what?
V du.
Yeah, v du. Actually, I don't really need that. V du minus 1 over x v du
Squared.
is 1 over x, and I can actually get rid of that. And then all of dx, and we have to go from 1 to b. Okay. So this is limit b goes to infinity of, all right, one more step. Minus ln x over x. What's this integrate to?
X to -2, right? So x to -1, -1 over x. I think.
Yeah, I believe it's -1 over x. And then we have to go from 1 to b. So before I continue, I'm just going to confirm that we're on the right track. I'd hate to do a lot of work for no reason. I think we're off by a sign. Integral v du. In my notes, I have it off by a sign. Okay, I don't think it will matter. Okay, does anyone see a mistake?
Wait, where's the sign different? The lawn? Or?
I have this as a plus in my notes.
Oh, okay.
So can anyone see a mistake?
Isn't it, it's UV minus the negative.
Yeah, but then there was a
But you took it out, so it makes sense.
Okay, so I'm just going to continue. Keep in mind that there may be a sign mistake. Okay, so now we just have to expand this. We're going to get limit b equals infinity minus ln b over b minus 1 over b minus, so that turns into a plus, ln 1 over 1 plus 1 over 1.
Can you factor out a negative? No, you can do that, right?
Well, let's not be too concerned about this sign. A lot of things are going to disappear anyways. Okay, so what we're left with here is that's a 0, that's 1, this is 0. Okay, so what about this?
Ln of infinity.
Over infinity.
Isn't that indeterminate?
Yeah, but what kind? It's a specific form. L'Hopital's rule. So by L'Hopital's rule, this is going to be 1 minus the limit of b goes to infinity of 1 over b over b over 1. L'Hopital's rule, which is 1 minus 0, which is 1. So there's a unit amount of area bounded by this infinite fence.
It's 1.
1. Isn't that neat? Right? That we can integrate over it. Like there's an infinite amount of stuff in here that is nonetheless finite. You could see this with fractal shapes, like snowflakes. If you try to measure the circumference of a snowflake, it will be infinite. But clearly, the snowflake has a finite amount of area. Right? So you can have infinite perimeter and finite area. There's bizarre things can happen in mathematics. And they occur in nature. That's the truly bizarre thing. Like you'd think that these would only be sort of tools of our imagination. Okay, this is indefinite integration. It's more or less it. Right? This notion that we can add a limit in an integral and take it. Okay, so now we're just going to do a bunch of other examples because we have to worry about other types of infinite areas. Like integrating through an asymptote is going to require some special treatment. And then I also have to give you a bunch of tools because will the area always be finite? Well, obviously no. X squared, 0 to infinity. Obviously we'll have an infinite amount of area. Right? So one of the things we need is for at least the function has to decrease to 0. Right? That will give us our first fighting chance of summing to something finite. Okay, let's do another example. Okay, so I have to define some notation now because the rule is if we do something again and again and again and again that it becomes annoying to write it down, we introduce new notation. So here's the new notation. You can go a to infinity fx dx. And this is a question asked on Piazza, so I'm just going to throw it in here. This is a symbol in math means it's equal because I say so. Right? It's definitionally equal. Right? You can't give any explanation to why this is the case because it's just a definition. And this is going to be equal to the limit n goes to infinity, or I should stick with my labels. B goes to infinity, a to b, fx dx. Right, so now I'm saying, look, I know this was illegal, but let's just define it to be this, so that this is no longer something illegal. It's kind of a dirty way around it by defining our way out of it. So obviously I can switch these, and you can get the infinity on the bottom. So if we do minus infinity to b of f of x dx, that's going to be defined to be the limit as a goes to minus infinity from a to b, fx dx. And then one more, which one is that, you reckon? What's one more thing I have to define? Exactly. The last thing that we're going to need is what this means. Okay, so this is the one tricky thing. So please perk up. You could be tempted, and it could work sometimes, to use one limit variable. So you can go to like n and minus n, but that somehow in some degenerate cases screws you. So we can't do that. When you see an integral, an indefinite one from minus infinity to infinity, what you have to do is just pick some constant and integrate to it, and just use that as a slice. All right, and then now you can use these definitions. Okay, so while I wipe down the boards, I want you to think about this example that we're going to do. I want to integrate 1 over square root x dx from 0 to 1. And I want you to tell me, well, first of all, the plot looks something like this. There's 0, there's 1. That's the area I want. So calculate it for me. I wipe down the boards. Or like, don't try to resolve it, but at least write down the limit that you need. Any predictions, finite or infinite? So be careful. We may only ask you to resolve that question. Right? So on an exam or a quiz, we can be like, is this a finite or infinite amount of area that's bounded? So for now, all of the techniques we have are actually going through the integration, but I'll show you some shortcuts. Okay, so what limit do I want here? Or what is the bounded area?
0 to 1.
We can't do 0 to 1. We never hit 1. Remember, one of the requirements for integration is that the function had to be continuous and differential, at least continuous over the interval. Is this continuous over the interval?
Wait, you said it doesn't hit 1?
No, it does. 1's not my concern. 0's my concern.
Yeah.
Right?
Oh. Nice.
There's a pole at 0.
Yeah.
And right there. Bad joke. Never mind. There's a pole at 0. We never hit it. 0 is not part of the domain of 1 over root x.
So how do we do this?
I said, give me a limit. We can't actually get to 0,
That's it.
but we can limit to 0, can't we? From what side?
From the right side.
Okay, so if I want to get that area, if I want to take that limit, this is actually going to be the limit. So it's b has to approach 0 from the left. of integral b to 1 of 1 over root x dx. That makes sense, right? I want to start forming rectangles by doing this. And coming from going right to left. And so this we'll say that I want to take the integral of 0 from the left to 1, which is fine.
Why is it from
What's
the
that
left?
from left?
Right, sorry, right, you're correct.
That makes more sense.
Yes, well the other one made no sense. So now we have no problem, right? Because we're now never asking to form a rectangle outside of the domain. We're forming rectangles arbitrarily close to 0, but not actually at 0. We don't even really care about that because we get to bypass all of the geometry by doing algebra. Okay, so let's resolve this. This is the limit b goes to 0 from the right of, what's the integral of this? Isn't it just root x, half? No, jeez, wrong way. 2 root x.
Here we go. From,
No, that's it, right? 2 root 2. If I take the derivative of this, I'm going to get 1 over root x. Because a 1/2 is going to come down and eliminate the 2.
you're absolutely
Okay, then you're going to have to do this from b to 1. So we're going to get what? Limit b goes to 0 from the right of 2 root 1 minus 2 root b from the right. So this is going to be 2 minus 0, 2. Okay, so the area bounded by that infinite perimeter is 2, which is kind of weird that something with infinite perimeter can have a finite area. It'll even get weirder when we start doing sums. So if I put a true-false question on your exam, that is it possible that something with an infinite perimeter has a finite area? You're going to answer yes, true. Well, don't joke. Don't you notice that sometimes when I pose these hypotheticals, those problems indeed end up showing up on your... Or maybe it won't. I don't even think there will be true-false on your exam.
multiple choice.
Multiple choice this time. Okay, I'm just going to recover my boards. Okay, so work on this one for the time being.
Yeah, sometimes they are.
Okay, never mind. I'm going to wipe down the board. I'm all kajiggered.
Yeah. Educated kids. Always.
Okay. So what about this one? The integral from 0 to 1 of 1 over 1 minus x dx. That's a function that looks like this. We should be going to infinity at 1. So we start at, hold on, this is 1 over x. Help me draw this. I know I have a pole at 1, but am I going to, so from the left, I have to go, from the left, it's going to be positive. Okay. So something like this. So I want to get this area. How do I get it? This is 1, this is 0, this is 1. Yeah.
From the left to 1?
Yeah, so I need to take the integral, so the bounded area here, it's going to be the integral from 0 to, I'm not allowed to write that. Oddly enough, we can't write 1 from the right in the same way we wrote infinity. I don't get to invent the rules, I wish I did. Okay, so this is limit. So b has to go to what? 1 from the left of 1 over 1 minus x. Oh, of the integral from 0 to b of 1 over 1 minus x dx. Okay, so what is the integral of this? 1 over 1 minus x. Okay, minus ln 1 minus x is the antiderivative of 1 over 1 minus x. We have to take this from 0 to b. So it's top minus bottom, so minus ln 1 minus b. Oh god, I forgot to write my limits. Okay, so this is going to be top minus bottom, so minus ln 1 minus b minus the bottom, ln 1 minus 0. Okay, so ln of 1 minus 0 is what? Ln of 1? Which is what? 0. So we don't care about this one. What about this? Well, b is approaching 1 from the left, which means the thing in here is approaching 0 from the right. So if I take ln to 0 from the right, what do I get? Well, how does ln look like? Yeah, negative infinity. And if I go to 0 from the right of ln of x, I get to negative infinity. Right, so this is going to be negative infinity with a minus. So we're going to get what? Okay, so it is possible to get infinite area. So it's not always the case that an infinite perimeter is going to bound a finite area. And it's not clear ahead of time what it's going to be. It's hard to guess, so we're usually stuck doing these integrals. And so I gave you two examples, one where we get finite area and another one where we get infinite area. So here's an exercise that's going to help you later on in the course. For what p, let's say in the natural numbers, does the integral, how did I set this up? 0 to 1 of 1 over 1 minus x to the p dx. When is this less than infinity? Okay, so here's a little piece of terminology. We're not really allowed to say this. If something is less than infinity, it's called finite, or it's also called convergent. This is the more appropriate terminology to use in this instance, right? Because we're accumulating a sum, right? The sum is stabilizing to some point. It's convergent. If something doesn't converge, it's called infinite. Or divergent. Okay, so just keep these pieces of terminology in mind. That if you're convergent, you're finite, and if you're divergent, you're infinite. I wrote it out a lot more, structured in the notes. Okay, so now we want to talk about convergence versus divergence. So we want to ask questions like, when is integral fx, right, convergent, or that is less than infinity? Okay, so you can always just go ahead and take the improper integral, right? And then you could ask. But it may be helpful to have a bunch of other tools. Did you guys have a question? No? Okay. Okay, so this is something called the direct comparisons test. And it's very easy, actually, although it requires sort of us thinking because there's a logic to it. Okay, so first you have when. I'm going to give you three functions. F of x, which is always positive, and always less than g of x. Right, so g of x is truly bigger than f of x. And let's just say that this is true for x in right? Just some infinite interval starting from A. Okay, if we know that f of x is always bigger than g of x, if I integrate over them, what's true about the integrals? Well, it is true that they're positive, but we can make a stronger statement. So I'll write it, and let's see. So if I have that this is true, and I do this, and I take any interval, b is greater than a, and I want to look at these two. Okay? Okay, so first of all, you notice this, okay, that the smallest the interval can be is 0 if it's always positive. What symbol goes in here? Well, I have a function, and I take the area under the curve. And then I have a function that's bigger, and then I take the area under the curve. Which one has more area? The larger one. So what symbol should I draw in between there? Less than or equal to. Did everyone follow that? Okay, that should be pretty obvious. Okay, but let's look what happens now. Suppose I know that this converges. What does that mean about this? Okay, I'll write one extra thing in. I know that this converges, which means that it's less than infinity.
So it's finite.
Huh? It's finite, yeah.
The other one must be finite.
So this has to be less than infinity, and thereby is convergent as well. Okay, so if it's the case that the integral from a to infinity of gx dx is less than infinity, is convergent, i.e. is convergent, this means that the integral of f of x dx from a to infinity is also convergent. We also had something called the limit comparison test, and this is very similar to it. Okay, I want to make another statement now. So what other statement can I make? Huh? Well, what happens if I know that this is divergent? Right? Means it's infinite.
So the other one must also be.
Yeah, so I'm going to draw something technically inaccurate. Like I can't write this, but this is what I mean. Right? I mean to say that this area is infinite.
It can't be greater than infinity. So
I
it
know.
must be
So it's,
equal.
well, it can't even be equal.
Yeah.
Don't make me write limits. Everyone knows what I'm trying to say. I found an instance of them writing infinity in the Thomas.
Yeah?
Yeah.
You get your $5?
Well, I don't know if it's wrong, but I should be like, ha, you did it. I should be allowed to do it as well. But this is why I put quotes, right? This means that I really should be using limits, right? But if this is moving to infinity and this is bigger than it, then this has to go to infinity, right? So thereby, if this is divergent, then g of x
This one.
from a to infinity
This one
has to be divergent as well. Okay, and I'll show you how to use this. Well, maybe I'll give you the question. Okay, because you're not always going to be able to take the integral, right, to answer the question. So sometimes you're going to have to use a trick in order to do it. So here's your question. Does the integral from 1 to infinity of sine squared x over x squared dx converge? So try to work that out. Okay, any ideas?
Where do we get g of x? If this is f of x?
Well,
Or this is the integral of f of x? Where do we
I don't know if this is convergent or divergent or not, so I don't know whether to make it the f of x or to make it the g of x.
What?
Okay.
Well, okay, so we have to notice some things here, okay? So first step is this, look. Didn't we do this already? Have we done this? No, we did something close. Can we do this?
Can we?
Assuming you said we already did it, then yeah.
Well, I'm saying it somewhat facetiously. Of course we can do this. You should be able to integrate this. So this is going to be b to infinity of what? What's the integral of this? Minus 1 over x. So this goes from 1 to infinity. So it's top minus bottom. Sorry, not 1 to infinity, 1 to b. So it's minus b, well, it's 0, right? That's what that's going to be. Minus 1. So this will work out to 1. Okay, so we know that this is convergent. Okay, so that's a good first step. Next, we notice, as we always sort of do, that this is between 0 and 1. This is always a great starting point when you see something with trig. It's usually trying to signal something to you. Okay, but what can I do this with? Like, what can I apply to this to get something closer to that? Well, what is the real one?
Divided by x.
Yeah, divide by x squared. X squared is always positive, so I don't have to worry about the signs changing. Right, so here you get 0 over x squared over sine squared over x squared is less than that. Okay, so this means that we have 0 is less than or equal to sine squared x over x squared is less than or equal to 1 over x squared. Okay, so now can you answer your question? What should we choose for f and what should we choose for g?
So g should be 1 over x squared, right?
Yes.
Or the integral.
Right? Well, let's not even do that. Right? Let's do this. Let's do, I know that the integral from 1 to infinity of 1 over x squared dx, right? It's greater than that, so I know that it's greater than this. Okay, hold on. Okay? If this is true, this, then this is true. Can everyone follow that? Right? I know that this function is always positive and less than that function. Thereby, the integral over any intervals on this is going to be less than the same interval over the integral over the same interval of this. Okay, but once I write down this, then it's easy to pull off the result that we need. Because I've already shown that this guy is less than infinity. What am I missing here to complete?
It's, greater than or equal to 0.
Why is this important?
It can't be negative. It can't be
Well, why is it important that I can't be? What am I trying to imply here? Right, that this sum is finite. Okay, and I'm saying, well, look, it's less than positive infinity, thereby it's finite. Is there a flaw in that reasoning? Can anyone give me an example of a non-finite number that's less than infinity?
non-finite number.
Something that is not finite and less than
I.
negative infinity. Negative infinity is still infinite. So something that, well, we technically can't have negative infinite area, but that's what we're seeing here. I can only conclude that this is finite because it's less than infinity, but nonetheless bigger than 0. It doesn't have to be 0. This could be negative 10 million. I just need it to stop. Right? This has to be something constant. It happens to be 0, which is good for us in this case, and obvious to why it should be 0. I can't integrate over an everywhere positive function and get anything less than 0. Okay, so here we can now say is convergent. Okay? So if I ask you to determine the divergence, convergence information about a bounded area on some integral that looks super complicated, just remember you have other tools to attack it. If we're asking you to only determine convergence, divergence information, you should always solve the easiest problem we give you. Right? Actually determining the limit of that function will indeed tell you the convergence divergence information, but it also tells you a hell of a lot of other stuff. The precise limit, for example. Okay, one more proposition. And then I'll let you guys go. So this one is called the limit comparison test. All right, the LCT. The limit comparison test says this: if f of x and g of x are both non-negative for x in an interval, this interval, an infinite interval. Okay, so then we have to look at a special limit. We need to look at the limit as b goes to, or well, here I say x goes to infinity of the quotient, or the division, the ratio of the functions. And this is going to be equal to some number L. And then we have to ask if this is bigger than or equal to 0 and less than and equal to infinity. Okay, so this is the precondition. You have two functions which are both positive. Notice that I've dropped caring about which one is larger than the other. I only care that they're both positive. If I find the limit of x goes to infinity of their ratio, and that ends up being L, and that L is finite. Jeez, it's a weird ring. If this is finite, then, right, so again, provided L finite, then, and this is a weird sort of statement, the integral of f of x d of x from a to infinity, and the integral from a to infinity of g of x d of x. Okay, and this is weird. Okay, if this is the case, then these integrals either both converge or both diverge. So this is a weird tool, kind of, but it says in order to find the divergence convergence behavior of a new indefinite integral, we could get lucky if that indefinite integral has an integrand whose ratio with another integrand is finite, and for which we know if this is convergent or divergent. This will make more sense with an example, so let's hit the example. So the question here is, does integral 1 over 1 plus x squared dx, what did I choose this over? 1 to infinity. Does this converge? Okay. So we always want to sample integrals that we know for sure converge and try to exploit that. So what did we learn about this? Oh, look, we just did this, didn't we? It was finite or infinite.
Finite.
This was finite. So recall, this is convergent. That is less than infinity. Okay, also notice this. Okay, so we're going to take a ratio of two things. first thing is going to be 1 over x, and the other thing is going to be 1 over 1 over x squared, 1 over 1 plus x squared. Right, that's the ratio that's in here. And what is this equal to? No, let's write out a little bit more. This is the limit of x goes to infinity of 1 plus x squared over x squared. So what is it? Please someone tell me the limit of this before I weep.
It's a determinant.
Oh no. We forgot all of this already? You guys got to start studying then, because limits are definitely going to be on the final. These ones are easy.
So it's 1.
It's 1, right? So I can break it up like this, and as x gets bigger, this gets smaller, so this will go tend to 0. So we end up getting 0 plus 1. Okay, so what does this tell us now, this theorem? What have I found? Well, I have two functions, f and g. Right? F is this. G is this. Right? So by the limit comparison test, I know that 1 to infinity of 1 over 1 plus x squared dx and 1 to infinity of 1 over x squared dx both diverge or converge. What else do we know? I wrote it down. It's the second thing I wrote down. Yeah.
That 1 over x squared is convergent.
Yeah, we also know that this is convergent. Okay, but this theorem tells us if this is convergent, then this has to be convergent as well. Right? So thus, by LCT, this is convergent. You have to write this. You have to specify the tool that you're using to get full marks. Well, theoretically. Okay, so let's review or recall what we learned today. We can take integrals over infinitely long intervals. Those require for us to introduce a limit. The limits for the infinities can go to positive infinity or negative infinity. If we're integrating through an asymptote, this is going to require us taking a left or a right limit. If you truly want to integrate through an asymptote, we didn't cover it, it is in the notes. Like suppose you want to integrate through an asymptote. You go to the left of the asymptote on the one side and to the right of the asymptote on the other side, and you just add them. Right? So indeed, you can go through an asymptote if you want. Okay, then we can ask you questions about the divergence, convergence, about individual integrals. And you have a shortcut or a method for handling these cases when the thing that you need to integrate is too hard. You then have to try to search for something that's easier to integrate that, determine its convergence or divergence, and then use one of these tests in order to conclude something about the other one. Right, this is very much like squeeze theorem and the comparison test on limits. Very similar. Any questions on this? Okay, so remember, do those 5 weekly work questions on probability, which all end up being an integral, and you should be prepared for your quiz. And otherwise, please study, especially if all of this knowledge on limits have been lost, because you're going to need to recover that for the final, which is fast approacheth. Anyways, you guys enjoy your weekend. Date was set for